Well, hello everybody. Right off the bat, I think you can see that there are two homework assignments associated with these notes. That's because in my old textbook, this was actually one unit, one lesson. In the new one, they split it into two, but they're so small, and I really don't like the way that the authors has split the information up. So this week, we're going to do it a little bit different. There's going to be the one lesson, and there will be two homework assignments associated with it. Still this one due Thursday and still this one due Sunday, but of course you're welcome to do them both ahead of time if you'd like to. But there it is. So it's just the one video. And before we get started, I'd like to take this time to give a special shout out to Avery's cousin. Apparently she is my biggest fan, and I hope that she has enjoyed the knowledge. Alrighty, so let's jump right into it. This unit 14.5, which I've split into two, is going to be called Shape and Inflection Points. So it's clearly two different things. First half will be about, well, first half, but the first kind of knowledge will be about the shape, and the other half of the knowledge will be about inflection points. So here, I've come up with a little diagram that shows you the general shape that curves can take. There are only four options. They could be up and to the left, up and to the right. These two things are known as concave up. They could be down and to the left and down and to the right. These two things are known as concave down. So what's going on here? Let's just start right here, because why not? What I'd like you to see is that any tangent line I draw here has a positive slope. So that tells you that everything right here has a first derivative that is positive. And using the same logic, this one here, every tangent line you draw would also have a positive slope. So again, first derivative is a positive number here. Okay, well, switch colors. Here, every tangent line you draw would have a negative slope. So your first derivative of this curve would be negative. And same thing's happening here. Every tangent line that you draw would have a negative slope, so first derivative is negative. So brand new knowledge. The second derivative is useful. You see, whenever a curve is concave up, as it turns out, the second derivative is positive. And when the curve is concave down, either one of these shapes, the second derivative is negative. There we go. And this concave up, concave down is what we will describe as the shape, quote unquote, of a curve. So let's talk about something that we've already talked about before, points of inflection. Well, a point of inflection is a point on a curve at which there is a change of the curvature, aka when the concavity changes from concave up to concave down or concave down to concave up. This is also known as a shape change. Well, here, we've already seen this image before. Here, first derivative is 0. Over here is concave up. So the second derivative is positive. And over here is concave down. So here the second derivative is negative. So what we have is a stationary point because the slope is 0 there. And it's also a point of inflection. And that's why we've been calling these things a stationary inflection point. This one right here at this point of inflection, where legitimately to the left of this dotted line, the curve is concave down, so second derivative is negative, and to the right of the curve, or to the right of the dotted line, the curve is concave up, so second derivative is positive. So yeah, this is a point of inflection, but you could see that the tangent line right there would not have a slope of 0. Looks like it would have a slope of -1. That's unimportant. The point is it's not 0. So we don't call it a stationary inflection point. Instead, we call it a non-stationary inflection point. And I just realized that this is hard to read, that was an N. There we go, stationary. So this would be called a non-stationary inflection point. Because remember, stationary means first derivative is 0. Since the first derivative is not 0, Well, it's non-stationary. You see, what I was just describing to you using first derivative and second derivative is actually known as the first and second derivative tests. So it's time to really be sure that you know your vocabulary and know what these vocabulary words imply. If the first derivative is 0, which we were looking at in the last 2 lessons, if the first derivative is 0 at any point, then that is known as a stationary point. First derivative is 0. F prime of x equals 0. Stationary. Now, if that first derivative happens to have a sign change at that point, well, you have a turning point. It could either be a local minimum or a local maximum. Okay, that's not new. But talking about the second derivative, this is where it gets new. So if the second derivative changes sign at a point, and by the way, the only way it could have changed sign at a point was if it was actually 0 at that point. So to the left it's negative, to the right it's positive, or vice versa. If you have a sign change on the second derivative, then what you have found is an inflection point. So how do you know if it's stationary or non-stationary? Well, if the first derivative is 0, stationary, and the second derivative changes point, inflection point, you have a stationary inflection point. Now, if a point is an inflection point, meaning the second derivative had a sign change at a point, but the first derivative was not 0 there, then you've automatically found a non-stationary inflection point because the first derivative wasn't 0. And then the textbook authors put this together in a tidy little Venn diagram for us. So turning points, let's start down here. Stationary points. Anytime the first derivative is 0, it's known as a stationary point. It could be a local max, it could be a local min, or it could be a stationary inflection point. These two are known as turning points because the first derivative is changing sign at that point. These are not turning points because the first derivative does not change sign. See, it's negative, negative, positive, positive. Now over here in this oval, these are inflection points. At every inflection point, the second derivative does equal 0. Let's be really clear here. Just because the second derivative equals 0 somewhere does not mean it is an inflection point. This is not a two-way street. The second derivative has to change sign to be an inflection point. But of course, every time you have a sign change, you had to have passed through a 0. Anyway, here and here, your first derivative is clearly not 0. This is a negative first derivative. This is a positive first derivative. So these would be non-stationary inflection points. And then again, concave up, concave down, stationary inflection. Concave down, concave up, stationary inflection. Boom. Okay, let's get to some actual examples. Got 2 right here, and it just says figure out where the curve is concave up and concave down. That means you're going to find the second derivative. And it actually doesn't matter what's going on with the first derivative, you just need the first derivative to find the second derivative. So for part A, f prime of x, or y prime, I guess I should say y because they didn't define it as f of x. Y prime is equal to, and it's just power rule straight across the board, 6x squared minus 6x plus 4. We haven't been asked to find any turning points or stationary points, so we're not even going to bother. We're going to jump straight to the second derivative now. Again, power rules are in place. 2 comes down, 12x minus 6. Now you set that equal to 0 and factor. Got a GCF of 6. Hold on, I'll be okay. I swear I'm smart. Try again. There it is. Okay, there is only one place where the second derivative could equal 0, and that's going to happen at x equals 1/2, because that's what's going to make the inside of those parentheses 0. So we're going to create a sign diagram for the second derivative. It has one x value on it, and then we check to the left and to the right. A very easy number to plug in that's to the left of 1/2 is 0. So if we drop a 0 right here, we just get 6 times -1. That's negative. And a really easy number to plug in after 1/2 is 1. Put a 1 right there, you get 2 minus 1, which is positive, times 6. Positive. So we have an inflection point at 1/2. We don't know if it's stationary or non-stationary because we didn't do the first derivative test. We didn't bother figuring out where the turning points and all this stuff were because we weren't asked to. We were just asked to find concavity. Okay, well, everything to the left of 1/2 would be concave down. I'm going to be really lazy and just say down. To the left of positive 1/2. And everything to the right would be concave up. Like so. Ta-da! Okay. Let's go to the next one. B. Oh boy. Well, it's a fraction. That means in order to find its first derivative, we are going to have to use the quotient rule. So we have u prime v minus uv prime all over v squared, where u is x plus 1 and v is x minus 3. Now the authors were nice to us here because both u prime and v prime are 1. Thank goodness. So we can fill out our quotient rule pretty darn quickly, actually. F prime of x, I can actually say f prime this time because it says f of x. F prime of x is u prime v minus u v prime. Now you have to be careful because it's minus. It looks like this. All over v squared. This minus sign gets distributed both to the x and the plus 1. So let's clean it up a little bit. We get x minus 3 minus x minus 1. Well, looky there. The x's are going to cancel each other out. Looks to me like it's just negative 4 over x minus 3 squared. Again, we weren't asked to find turning points or anything like that, so we're just going to go straight to our second derivative. But in order to find the derivative of this, I kind of want to avoid the quotient rule if I can. So before I find the second derivative, I'm going to rewrite the first derivative with negative exponents. So negative 4 times x minus 3 to the negative 2. So finding the second derivative is going to be very, very easy because check it out. The chain rule is not actually in play here because the derivative of the inside is just 1. So we don't have to do the chain rule. So we're going to bring this negative 2 down to the front. It's going to give us 8. And now we get to decrease this by 1. So we get 8 over x minus 3 cubed. That is our second derivative. Okay, looking for critical values. Well, this fraction can never equal 0. It's not possible because the only time a fraction can equal 0 is if the top equals 0, but the top is 8. But just like with the first derivative, critical values are going to happen anywhere you get the derivative equal to 0 or the derivative is undefined. And x equals 3 is a no-no. X equals 3 is a place where our second derivative is undefined. So we do have to build a sign diagram around x equals 3. Now, if you look at the original thing, x is not allowed to be 3. I mean, at x equals 3, you have a vertical asymptote. So it can't be an inflection point because it's a vertical asymptote. Now let's check the signs. Well, you know what's to the left of 3? 0. 0 minus 3 is negative. If you cube it, it's still negative. Any number to the right of 3, like 4. 4 minus 1 is positive. If you cube it, it's still positive. Boom. Just like that. So we are concave down everywhere to the left of 3. And we are concave up everywhere to the right of 3. Ta-da! All right. Push to the side. That's the back. Sorry. Is that the top question? It is. Cool. So we've been tasked with finding and classifying all of the inflection points. That means we need to know, was it a stationary inflection or a non-stationary inflection? Well, inflection points are found by the second derivative, which means we're going to have to go through the first derivative. First derivative looks like 4x to the third minus 12x squared. Well, just because it's good practice, I'm going to go ahead and figure out what the stationary points are by factoring this. It looks like 4x squared is the GCF, leaving an x minus 3. So our stationary points are at x equals 0, because, right there, and x equals 3. Those are stationary. Okay, now let's find our second derivative. So finding the derivative of this, I'm not going to look here, I don't want to use the product rule. So finding the derivative of this, again using power rules, bring the 3 down, the 2 down, you're going to get 12x squared minus 24x. And we set this equal to 0 and factor. Because anytime you have an inflection point, the second derivative must have equaled 0 there. So we're looking for critical values on our second derivative. 12x is the GCF, leaves you x minus 2. So the critical values here are x equals 0 and x equals 2. All right, I'm going to draw a sign diagram for the second derivative. And let's see what's going on. Let's plug in a negative number. That's going to be negative when I plug in a negative number, and so was that. And when you multiply two negatives, you get a positive. Let's plug in a number between 0 and 2, like 1. 12 times 1 is positive, 1 minus 2 is negative. Positive times negative, negative every time. And plug in a number bigger than 2, like 3, positive, positive, positive. So there are 2 inflection points, and the reason why there's 2 is because I have 2 sign changes on the second derivative. So what's happening at x equals 0? Well, we know it's an inflection point, but guess what? It was also stationary. It was a place where my first derivative was also 0. So since it showed up in the first and second derivative, this is a stationary. Did I spell that right? I think so. A stationary inflection point, IP. But x equals 2 did not show up in the first derivative. That means x equals 2 is not stationary. X equals 3 is, but x equals 3 didn't show up in the second derivative. So these have nothing to do with each other. All that matters is that this guy was not present as a critical value on the first derivative. That means this is a non-stationary inflection point. And there you have it. So what does that tell you about x equals 3? Well, because it was not an inflection point, it is automatically going to be a turning point. And if you don't believe me, you're welcome to do the sign diagram for the first derivative. Next. Oh boy, 2 minus e to the negative x. Do not write large for this. I'm not going to lie. This is kind of a small amount of space to do this amount of work that we're about to do, so don't write large. First thing we've been tasked with is finding the x and y intercepts. Well, that's pretty easy. That basically just means plug in 0 for x, see what happens, plug in 0 for y, see what happens. So for the x-intercept, when you're on the x-axis, y equals 0. So solve for x. Add e to the negative x to both sides. And then you cancel e on both sides with ln. So negative x equals the ln of 2. And then, of course, you divide it by negative 1. So x equals negative ln 2. I mean, it's not a pretty number, but it is a number. Alrighty, let's, how about our y-intercept? When you're crossing the y-axis, x equals 0. That's going to be really easy. So it's just 2 minus e to the 0. I forgot to write y equals. Bad mathematician, bad. Y equals 2 minus e to the 0. Anything to the 0 power equals 1. So you're crossing the y-axis at y equals 1. Okay. Where are we at? Part B is to show algebraically that the function is increasing. That means always positive slopes. So what we've been told to do is show that the first derivative is always positive. Okay, no sweat, we got this. B, y prime. equals. Well, the derivative, excuse me, I just got these lips. The derivative of every constant is 0. So we're not going to worry about that. And so we write, I'm trying to find the derivative of this basically right here. The derivative of every exponential works the same way. You write the original exponential, and then you multiply by the derivative of the exponent, which here happens to be -1. This is the chain rule. So y prime is e to the negative x. Well, e is a positive number. It's not a pretty number, but it is positive. So it doesn't matter what power you raise a positive number to, because you're always going to get a positive number as a result. So there you go. You have just shown algebraically that this function is always increasing. No need for a sign diagram. Part C says to show that the function is concave down for everything. Well, concave down implies that the second derivative is negative, so we actually have to find the second derivative. Y double prime. We're finding the derivative of this. Remember, when finding the derivative of an exponential, your job is to write the original exponential and then multiply by the derivative of its exponent, which is still -1. Boink! And there you have it. I mean, e to any power is always going to be positive, but then you throw this negative sign in front of it, and, well, you've just shown that y double prime is negative. And since y double prime is negative, this is concave down. Y double prime less than 0. So, concave down. I'm being lazy with the CC, concave. I shouldn't do that, but, you know. What's next? Part D says use technology to graph the function. Okay. Well, I'll save you the trouble. If you had grabbed your graphing calculator, it would have looked like this. Picture not drawn to scale, ever. We know that we are crossing the y-axis at 1, and we know we're crossing the x-axis at -ln2. So let's say this is 1, and let's say that this is -ln2, because why not? And this is going on. Now, of course, your graphing calculator won't show you the red dotted line. It's not part of the actual curve. The actual curve looks something like this. You see, this is a horizontal asymptote. Part E asks you to explain why y equals 2 is the horizontal asymptote. And in order to do that, we're going to use some limits. So E, the limit as x approaches infinity, because remember, horizontal asymptotes are always results of approaching infinity, and you can see as I go to the far right, I'm getting close to this line, of my function. We go, well, this is the same thing as saying the limit as x approaches infinity of 2, which is just 2, minus the limit as x approaches infinity of e to the negative x. But remember, e to the negative x, since it has a negative exponent, can be written as 1 over e to the x. And when you drop an infinity right here, you have e to an infinity, which is just infinity. So what you have here is a constant divided by infinity, which will automatically go to 0. Which means you're just left with the limit as x approaches infinity of 2, which is just 2. Boom. And lastly, hopefully you were able to fit all that on there. Lastly, we go to here. Oh man, it's longer than I thought. There we go. Okay, so we have this fourth degree polynomial. First, we're going to find and classify all of the stationary points. Meaning, are they turning points? Are they stationary inflection? Is it a local max? Is it a local min? Things like that. So part A, looking for first derivative. F prime of x is 12x to the third minus 48x squared plus 48x. Okay, I got this. I got this. Before I move any further, now you know what? We'll just keep going with it. We know we're going to have to set it equal to 0, and we're going to have to factor. Seeing a GCF of 12x. And the two numbers that multiply to be positive 4 and add to negative 4 are negative 2 and negative 2. So we have two stationary points, two critical values from the first derivative, one when x equals 0 and the other when x equals 2. Time for a sign diagram. Let's plug in a negative number. Guess what? It doesn't matter what you plug in here. Because it's squared, this thing is always going to be positive. So if we plug in a negative number, we have negative times positive. Now if you plug in a number like positive 1, you get positive times positive. And if you plug in a number like 3, you get positive times positive. So what was going on here? Well, because my slopes changed from negative to positive here, I have a turning point. More specifically, negative slopes to positive slopes. I have a local minimum. X equals 0 is a min. And right here, I didn't have a change in slope. So x equals 2 is automatically a stationary inflection point. It doesn't have a choice. That was something that we've already talked about. Now let's go ahead and do part B. Part B is to find and classify all the inflection points. Well, we already know one. One of the inflection points happens at x equals 2, and we know it's stationary because the first derivative was 0 there. But let's be good little mathematicians and find all the other ones. So let's go to find the derivative of f prime. F double prime gives me 36x squared minus 96x plus 48. The GCF here is 12. And yeah, this does factor. I'm just going to assume at this point that you know how to factor in one method or another, so I'm not going to review that. I'm just going to write what it is when it's factored. Should get 3x minus 2 and x minus 2. Like that. So we have two critical values on the second derivative. Now that doesn't mean that they're both inflection points. Remember, second derivative equals 0 does not imply inflection point. Second derivative equals 0 just means it could be an inflection point. But if something is an inflection point, I'm going the other way on the street now, if something is an inflection point, by definition, the second derivative had to have equaled 0 there. You see, something is not an inflection point unless the second derivative changes sign. So we have two critical values, one at x equals 2/3 and one at x equals 2. Well, we already know what's going on there because, you know, spoiler alert, it's right there. So we already know that this is a stationary inflection point. But I'm going to go ahead and draw the sign diagram anyway because I don't know. Is this even an inflection point? We don't know. So because it is possible to have a second derivative equal 0, but it not to be an inflection point. Just ask my current seniors. They watched me bog down an entire lesson because I couldn't figure out what went wrong. And it's because I had a second derivative that equaled 0 that wasn't an inflection point, and I didn't catch that, and it took like 30 minutes to figure out what I did wrong. So it is absolutely possible for the second derivative to equal 0 and it not to be an inflection point. Let's plug in a number to the left at 2/3. A really easy value to plug in here would be 0 because that's going to give you negative times negative. Something between these two that you can plug in is 1. Plug in a 1 here, you get a negative, but you get a positive here. And then plug in, say, 3. Positive, positive. Cool. So, yeah, this is an inflection point because I had a change in concavity. But because it was not a stationary value, it is a non-stationary inflection point. I'm being really lazy in writing INSIP and things like that. I really shouldn't be doing that. And we already knew that x equals 2 was a stationary inflection point. I'm being really lazy. That is not normal mathematics. No other person would even know what that means if you wrote it. I just am being lazy. Part C. It says, where's the function increasing and decreasing? Oh, well, that's coming from right here. So for C, we are increasing when our first derivative was positive. So from 0 to 2, and also from 2 to infinity. We are decreasing to the left of 0. There it is. Part D says, where's it concave up, where's it concave down? Well, that's coming from this one, D. So where are we concave up? Everywhere the second derivative is positive. So to the left of 2/3 and to the right of 2. And we're concave down between those values. Part D is finished. The hardest part, part E, sketching the function, showing features that you found. Here we go. E. There are 4 x values that mean something to me. Here they are. Oh, excuse me, 3. I forgot, this one's repeated. 3 x values that mean something important to me. So we're looking at x equals 0, x equals 2, and x equals 2/3. Picture not drawn to scale. It's never drawn to scale. Drawing it nice and big. Oh, you can't even see what I'm drawing. Nice and big here. Okay, so you got x equals 0, obviously at the origin. I have an x equals 2 and an x equals 2/3. So if this is 1, this would be 2. And 2/3 would be somewhere around right here. Okay. Also, just because we can, if you, man, where is it? There it is. If you plug in 0 right here, you get the y-intercept as -9. So, I mean, we might as well throw it on there. Because something is going to happen at that x equals 0. That was a minimum value. It actually happens to be at -9. Okay, awesome. Here we go. So, what did we know? Let's scoot these sign diagrams. Now, I can't get the sign diagrams, but I can get this information. I know that I had a positive slope everywhere to the left of 2 because it's increasing. Not everywhere to the left of 2. I'm sorry, from 0 to 2 and then everywhere to the right of 2. That's what I meant to say. Because at 2, we had a stationary inflection point. So it had to have looked like this at that value. And at 2/3, we had a non-stationary inflection point. So it had to have looked like this at that value. It didn't have a choice. So we're just going to get to sketching. I know I have a minimum value at 0, -9. And to the left of 0, my slope is negative. Looks something like that. Now, I'm increasing after 0 until I get to 2. Whoops. But then I stay increasing after 2. So, I don't know, somewhere over here at the 2 mark, I'm going to do this. No, I don't know this y value. I arbitrarily chose a y value. We know we have a stationary inflection point at 2. And I realize I just stretched this thing out way too much, but hey, you know what? It is what it is. So this was flat, and then I didn't have a concavity change until 2/3. So I was concave up everywhere until 2/3. So it looks like this, and then magic, like that. So right here-ish is where our non-stationary inflection point was. Right here, this was our stationary inflection point. Right here, at x equals 0, was our minimum turning point. And there you have it. You have successfully sketched the curve. Again, y values are a little jacked up. My stretching from left to right is a little goofy, but you get the idea. And that's everything there is to it. I know the notes are long. I am so sorry, but think of it like this. You don't have to listen to me again this week unless you want to pop on Zoom with me. That being said, if you need me, let me know and we'll Zoom. Alrighty, guys. I'll talk to you later. Have a good night or morning or afternoon. I don't know what time of day it is for you.